We have been discussing dynamics of continuous systems. Towards the end of the last lecture, we reviewed the analysis of continuous systems under deterministic load. So, we considered as an example the dynamics of an Euler-Bernoulli beam whose equation is displayed here. The first term here is the stiffness term. This term is the inertial term. This is there are two damping terms. One is C of x into y dot. This is velocity dependent damping. This is strain rate dependent damping, and f of x comma t is the external force. These are the initial conditions, and boundary conditions as appropriate have to be specified. And we assume that this epsilon of x is proportional to the flexural rigidity, so that this damping term will be proportional to the stiffness of the system. We first carry out an undamped free vibration analysis and determine the normal modes. Here these are the eigen functions phi n of x, and they are governed by this equation. This is the eigenvalue problem, and the eigen functions satisfy this pair of orthogonality relations, one with respect to flexural rigidity, where the second derivative of the eigen functions are involved, and the other with respect to the mass function, where phi n of x and phi k of x are involved. And we expand the solution to the forced vibration problem in terms of the generalized coordinates a n of t and phi n of x. This n runs here from 1 to infinity, and the governing equations for a n of t turns out to be of this form: a n double dot plus 2 eta n omega n a n dot plus omega n square a n is p n of t. P n of t is the generalized force given here, and this damping term 2 eta n omega n is expressed in terms of the for the proportional damping model that we are assuming, it will be in terms of two constants alpha and nu and omega n square. The mode shapes for the eigen functions for a simply supported beam we saw to be sine functions. The first mode is a half sine wave, second one is one complete sine wave, and so on and so forth. So, alternate eigen functions are symmetric with respect to midspan and antisymmetric with respect to midspan. So, we have reduced the given partial differential equation into a infinite set of single degree freedom system, each one of which can be solved using the methods that we have already learnt, and based on the solution for a n of t, the expression for the displacement function can be expressed in this series form. So, the first terms here shown in the bracket here are the contributions from initial conditions, and this is the particular integral in terms of the Duhamel's integral associated with each one of these single degree freedom systems. Once we find displacement, we could go ahead and evaluate the slope, which is the derivative of y x comma t. Here we need phi n prime of x, and bending moment, which is E I of x into y double prime x comma t as shown here, and shear force, which is the derivative of the bending moment shown here, and other quantities like bending stress, shear stress, and principal stresses at any point can be eventually evaluated. Here we are summing, the summation should run from n equal to 1 to infinity, but typically in numerical work we stop at some finite capital N, and the rate at which this series converges is different for displacement, slope, bending moment, and shear force. Typically lesser number of terms are needed for convergence of displacement, and higher number of terms are needed for shear force. We will continue with this discussion now, and we will see how to analyze problems of single span beams if excitations appear as support motions. This is typically what would happen in an earthquake engineering problem. So, to illustrate that, we consider a single span beam which is clamped at the two ends, and the two supports are subjected to displacement u of t and v of t. The field equation here, we are assuming a simpler model for damping, and we are also assuming that beam is homogeneous. So, we get E I y 4 plus m y double dot plus C y dot equal to 0. The excitations u of t and v of t appear as boundary conditions, that is y of 0 comma t is u of t and y of L comma t is v of t. Since the beam is clamped at the two ends, we get y prime of 0 comma t is 0, y prime of L comma t is 0. We also assume for sake of simplicity that this beam starts from rest. Now, a complicating feature here is that the boundary conditions here are time varying. So, consequently, we will not be able to use the eigenfunction expansion method to solve this problem. So, we overcome this difficulty by implementing a transformation of the dependent variable and we introduce a new dependent variable w and relate it to y of x comma t through this relation. Here w is the new dependent variable, h1 of x and h2 of x are unknown functions which we need to determine, and u of t and v of t are the support displacements. So, now you look at boundary condition at x equal to 0, we get y of 0 comma t is w of 0 comma t plus h1 of 0 u of t plus h2 of 0 v of t, and this must be equal to u of t. We can satisfy this requirement by taking w of 0 comma t as 0 and h1 of 0 as 1 and h2 of 0 as 0. Similarly, the condition y prime of 0 comma t can be satisfied by taking w prime 0 comma t equal to 0, h1 prime of 0 is this should be 0 and h2 prime of 0 is 0. Similarly, we satisfy boundary condition at x equal to L and put condition on displacement and condition on slope. We will get now there are two functions h1 and h2. For each one of these functions we get 4 conditions at x equal to 0 and at x equal to L. Now, if we substitute this assumed solution form of the solution into the Gaussian equation, I get E I w 4 h1 4 u plus h2 4 u and m w dot w double dot and so on and so forth equal to 0. Now, what we do is we select h1 4 and h2 4 to be equal to 0, and consequently, for example, for h1 of x I get a cubic polynomial with 4 constants and I have 4 conditions specified on h1. Using that I can determine these 4 constants a, b, c, d, and if we do that we get this function h1 of x is 1 minus 3x square by L square plus 2x cube by L cube as shown here. Similarly, we can use h2 of fourth derivative of h2 equal to 0 would mean again h2 of x is again a similar cubic polynomial similar to this, and then again on h2 I have 4 conditions. Using that we can show that h2 of x is another cubic polynomial as shown here. If we were to plot them, they look like this, h1 of x is this and h2 of x is this. So, if you are familiar with finite element modeling of beam elements, you will recognize that these are nothing but 2 of the shape functions that we use in discretizing beam element. So, with this we now go back to the original field equation, h1 of 4 is 0, h2 4 of 0 is 0. So, I get E I w 4 m w dot c w dot is equal to the remaining non-zero terms are put on the right hand side, and this the quantities on the right hand side are given. M is known, u double dot is known, v double dot is known, c is known, u dot is known, v dot is known, so on and so forth, and I call this right hand side as f of x comma t. In this analysis now, if you look at the boundary conditions on w, we see that the boundary conditions here become time independent. So, w of 0 comma t is 0, w prime 0 comma t is 0 and w of L comma t is 0 and w prime L comma t is 0. We could of course derive the initial conditions as well, and this problem is now amenable for eigenfunction expansion method, and we can proceed and solve this problem. So, what we are doing is the given problem where the excitation appear as time dependent boundary conditions, through this transformation we are converting this problem into an equivalent problem where the beam now carries a hypothetical load which varies in space and time, and the displacement of this is W not Y, and this W is related to Y through this equation where W is solution of this, U and V are given support displacement, and H1 and H2 we have selected suitably. So, we can look at the transformation that we have done is amenable for an interpretation. This y of x comma t can be viewed as a total response and W as a dynamic response, and the term inside this bracket is the pseudo dynamic response. This is analogous to what we did for discrete multi-degree freedom systems. That is, in this structure, without the inertial terms participating in the solution, we still get certain displacement and stresses in the beam due to differential support motions, and that is a pseudo dynamic response where inertial effects and damping effects are not included. This is a dynamic component where inertial components are also included, but the supports are now not moving. So, this is, as I already said, is analogous to what we already saw when we studied discrete multi-degree freedom systems which undergoing differential support motions. We are eventually interested in analyzing the response of the beam to random excitations. So, to prepare the basic formulations to achieve that, we need to consider a few deterministic problems. One is the problem of a harmonically driven beam. We consider this beam, the boundary condition here is shown to be hinged at the two ends. The beam is hinged at the two ends, but this is just for illustration, it can be any other boundary condition as well. So, we assume that this beam is driven harmonically by a force e raised to I omega t applied at distance psi from this end, and we are interested in knowing the displacement at a point x at a distance at this point, which is at a distance x from this left end. So, the Gowning equation here is displayed here. The left hand side remains the same. Now, on the right hand side we apply the force e raised to I omega t, and this is a concentrated load applied at x equal to psi. Therefore, I represent that by using Dirac delta function delta of x minus psi. We assume certain initial conditions, and the boundary condition appropriate for this end condition shown here is that displacement is 0, bending moment is 0 here, and similarly displacement is 0 and bending moment is 0. We are interested in solution of this problem as t goes to infinity. That means, we are basically interested in investigating the harmonic steady state of the Euler-Bernoulli beam. So, we can expand the solution in terms of eigenfunctions phi n of x and generalized coordinates a n of t, and this phi n of x satisfies this equation and these orthogonality relations with respect to E I and m. Using this, now we can derive the equations for the generalized coordinates, and on the right hand side the generalized force is now given by 0 to L e raised to I omega t phi n of x delta of x minus psi dx. So, this integration can be carried out in a straightforward manner. So, we replace x by psi and I get phi n of psi exponential I omega t, and this is true for n equal to 1 to infinity. So, the given partial differential equation is thus equivalent to a family of single degree freedom systems, each one of which is driven by e raised to I omega t, and the magnitude is given by the value of the mode shape at the drive point. This can easily be solved. We know how to get a n of t as t tends to infinity. So, we get t tending to infinity, a n of t is phi n of psi e raised to I omega t omega n square minus omega square plus I 2 eta n omega omega n. Now, if we now substitute this solution into the expression for y of x comma t, I get phi n of x into a n of t. Phi n of x is here and the remaining terms are the a n of t which I have derived just now. This summation, I write this solution as g of x comma psi comma omega e raised to I omega t, where g is given by this summation. This function is known as the Green's function for the beam. It is function of the point where you are measuring the response, the point where you are driving and the driving frequency. It is a complex valued quantity, it has an amplitude and a phase, and it is actually it is symmetric in x and psi. This is actually a manifestation of reciprocity theorem. The Green's function is symmetric in x and psi. It is complex valued, and this is actually the generalization of the frequency response function matrix that we consider for discrete multi-degree freedom systems. We had there a n by n matrix, now it is a function in x and psi. So, the Hij of omega that we used in discrete multi-degree freedom system, now this role of I and j is played by x and psi here. A typical Green's function when measurement point is 0.3 L and drive point is 0.3 L is shown here, and we see here that the amplitude of the Green's function, this is actually the amplitude, peaks at the system natural frequency. These are actually the system natural frequencies, and between the two modes there is a characteristic minima. So, here what happens is the contribution, suppose you are driving here, the contribution to response is predominantly from this mode and this mode, and they add up and produce a small quantity, and that appears as a minimum. Now, if you drive at a different point than where measurements are made, that means now you measure at 0.4 L, but drive at 0.3 L. Here again the frequency response function peaks at the natural frequencies, but between the two modes there is now a different kind of behavior possible. Here what happens is, again if you drive at this frequency, the response is mainly made up of contributions from this mode and this mode, but here what happens is the contribution from this mode cancels with the contribution from this mode, and we get an anti-resonance point. Whereas here if you see, the contribution from this mode and this mode add to produce this value, and they are of the same sign. Therefore, we get this characteristic minima, whereas this is a sharp anti-resonance point. This actually does not go to 0 because there will be contribution from other higher modes which will be small and yet, but not 0 anyway. Okay. So, another thing that you should notice here is that the beam natural frequencies, you know, as you go higher up in the frequency, the spacing between frequency increases. In fact, this increases linearly. This is a property of a Euler-Bernoulli beam. If it were to be an actually vibrating rod, these peaks will be uniformly spaced, and if it is a membrane or a shell, these peaks come closer as we go higher up in the frequency, and this frequency response function tend to become smooth. We will return to that point later when we briefly discuss what are known as statistical energy analysis methods. So, this is another plot of amplitude of frequency response function. Here drive point is quite removed from the excitation point, and we see that here there are more anti-resonance points. This is one of the, again one of the properties of Green's function. If drive point and measurement point move away, there will be more anti-resonances in the response. Now, equipped with now the definition of Green's function, we will now consider the response of the beam to a general force f of t, and we will perform the analysis in frequency domain. So, the field equation is the left hand side is the same, the right hand side is f of t into delta of x minus psi. In the example that we just now discussed, f of t was e raised to I omega t. Now, it is a more general function f of t. We will assume that f of t admits a Fourier representation, that means its Fourier transform exists, and we are interested in the Fourier transform of the response quantity y of x comma t. It can easily be shown that the Fourier transform of y of x comma t is given in terms of the Green's function g of x comma psi comma omega into the Fourier transform of f of t, which I have denoted as f of omega. This is quite similar to our input output relation in frequency domain that we have derived for single degree freedom systems and multi degree freedom systems. So, this is a generalization for a continuous system. This G here, just to emphasize again, is obtained as an series made up of infinite number of terms, each term coming from one of the normal modes. Now, we will look at these problems in time domain. Instead of applying now a unit harmonic load, if I were to apply a unit impulse load at x equal to psi, and again ask the question, what is the response at this point x, at a distance x from this end. So, on the right hand side here I get an impulse applied at t equal to 0 and at x equal to psi. So, that is represented as product of two Dirac delta functions. So, we assume that system start from rest. So, initial displacement and initial velocity are 0, and again the boundary conditions are displacement and bending moment are 0 here and here. We can again use the eigenfunction expansion representation for the solution. A n of t are the generalized coordinates, phi n of x are the eigenfunctions which satisfy these orthogonality relations, and the equation for the generalized coordinates is displayed here, and on the right hand side the generalized force is obtained as 0 to L phi n of x delta of t delta of x minus psi dx. So, one of the integration with respect to x now can easily be carried out. We replace x by psi and write phi n of psi into delta of t. So, now each of these single degree freedom systems is now driven by unit impulse, an impulse applied at t equal to 0, and its amplitude is given by the value of the mode shape, the nth mode shape evaluated at the drive point. So, A n of t consequently will be phi n of psi into h n of t, where h n of t is the response to a unit impulse response function. This is a unit impulse response function. So, A n of t is given by this. We are assuming system to be all the modes to be under damped. So, we write the impulse response function for the nth generalized coordinate as 1 by omega d n e raised to minus theta omega n t sin omega d. The generalized mass here m n is 1, because that is how we have normalized the eigenfunctions. So, we are taking 0 to L m phi n square of x dx as 1. Therefore, this m n does not appear here. We will now substitute a n of t into the series expansion for y of x comma t, and we get this function. This function is again known as Green's function, but it is Green's function in time domain. It is again a function of drive point and measurement point. Now, it is a function of time. It is again symmetric in x and psi, that is g of x comma psi comma t is g of psi comma x comma t. That means, if you interchange the drive point and measurement point, the Green's function will not change. This is a plot of Green's function when the drive point and measurement points coincide and both are equal to 0.3 L. You can see here that initially the response is made up of different frequencies, and eventually it seems to be decaying at the same frequency, a single frequency. That means, in free vibration the beam oscillates. The beam oscillation is made up of contributions from several modes typically. This is drive point is 0.3 L and measurement point is 0.4 L. Again the characteristic exponential decay is seen. This is another variation, the drive point is 0.3 L and measurement point is 0.9 L, and we can see here the contribution from different more than one mode is evident, especially for response near t equal to 0, where we are applying the impulse. Now, if we now apply a force f of t at x equal to psi, and I want to now characterize the time history of response, say the displacement at this point. Just now we analyzed this problem in frequency domain, we are now considering problem in time domain. So, the beam equation, the right hand side changes, now it is f of t into delta of x minus psi, and we are assuming that system starts from rest, and we can show that the displacement y of x comma t is actually the convolution of Green's function appropriate for this psi and x, and this convolves with the time function f of t to give me the displacement y of x comma t. So, this is analogous to our x of t is equal to 0 to t h of t minus tau f of tau d tau that we have seen for single degree freedom system, and for multi degree freedom system we had impulse response function with indices h, I, j, right. Now, the role of I and j are now played by the independent variables x and psi, which take values between 0 and L now. Now, I suggest an exercise. You can show that the Green's function in time domain and Green's function in frequency domain form a Fourier transform pair. So, this is again analogous to the result that we have shown, that impulse response function and frequency response function for a discrete single degree as well as multi degree freedom system form a Fourier transform pair. That means, what you need to show is this G and this G satisfy this pair of equations. We will now consider what happens if the beam carries a general load f of x comma t. So, on the right hand side I have f of x comma t, and we are assuming that system starts from rest. So, in time domain we can derive the response in terms of the Green's function as shown here, and in frequency domain we can derive the Fourier transform of the response in terms of Green's function in frequency domain. So, this is basically the input output relation in time and frequency domains for a deterministic system subjected to a general load f of x comma t. This again requires a few steps of derivations. I will leave this as an exercise. Now, we will consider the problem of beam subjected to random excitations. To start with, we will consider the problem where the beam is driven by a random process f of t at a point x equal to psi, and we are interested in response y of x comma t. So, the governing equation, this remains the same, this is a sample equation for sample of f of t, and this f of t itself we assume that its mean is 0 and it is a stationary random process with autocovariance function RFF of tau, and associated with this we have the power spectral density function SFF of omega. We assume that the system starts from rest and the boundary conditions as appropriate are mentioned here. So, we are interested in finding out mean response, autocovariance of the response, and covariance of the cross covariance of the response at different points. Here I have y1, it is y2, what is the covariance between the two? What is the power spectral density function of y of x comma t? What is the cross power spectral density function between response here and response here? So, such questions can be posed, and we need to find answers to these questions, and we need to formulate the problem in time domain and frequency domain. So, we will see how I will show a few of these formulations. Now, we start by writing y of x comma t in terms of the Green's function, convolution of Green's function with the applied f of t, and if you take now the expected value of this, this is the expected value of f of tau is 0, therefore, this is 0. What happens to the covariance between response at x equal to x1 and x equal to x2 and time t equal to t1 and time t equal to t2? So, we need to find the expectation of we need to evaluate this integral where the expectation of applied force appears here. This is a stationary random process. So, RFF of tau 1 comma tau 2 can be written as RFF of tau 1 minus tau 2. We already derived the Green's function in terms of the natural frequencies and mode shapes of the system, modal damping, natural frequencies and mode shapes. So, that can be plugged here and these integrals can be evaluated to determine these requisite moments of the response. We can of course write the response also in terms of power spectral density function of the input. To see that, what we do is I represent RFF of tau 1 comma tau 2 in terms of its Fourier transform, one sided Fourier transform, which is shown here, and we interchange the order of integration. So, we first integrate with respect to tau 1 and tau 2 and define a function capital H, which is this double integral in terms of system Green's functions and this cosine function. This can be viewed as the generalized transfer function, which is function of space as well as time. So, I get the cross covariance between y at x1 and y at x2 to be given by this expression. If we want mean square value, what I have to do is I have to put x1 equal to x2 to x and t1 equal to t2 to t, and if you do that in this expression I get xx psi t comma t omega dy. So, this gives me the variance of displacement. So, the key to this evaluation is actually the evaluation of this double integral, and this contains the eigenfunction expansions for Green's function in terms of natural frequencies, modal damping and mode shapes. So, this in principle can be evaluated. If we are interested in steady state response, we can look at the response in frequency domain and we consider the Fourier transform of a truncated sample of y of x comma t, and that is given in terms of a truncated Fourier transform of a truncated sample of excitation through this relation. And we know that power spectral density function is defined through this expectation as t tends to infinity, and if we apply this we get the input output relation, that is the response power spectral density function at x due to driving at psi is given by the amplitude of Green's function squared into SFF of omega. This analysis of course we can repeat for different values of x, that means you can find out the cross power spectral density function between response at x equal to x1 and response at x equal to x2. We now consider another example. We consider the beam excited by what is known as rain on the roof excitation. This is a space time white noise having certain special properties. The equation is here, the right hand side is f of x comma t, left hand side remains the same. Now, the property of f of x comma t is that the mean is 0, expected value of f of x comma t is 0, but if you find the covariance between f of x comma t and f of x plus psi and t plus tau, this is given by an intensity parameter I naught of x, I naught, and this m of x, which is this mass here, and delta of psi into delta of tau. This type of excitations are known as rain on the roof excitations. This is used in response of structures to say boundary layer turbulence and in problems of high frequency vibration analysis, at some point we will return to this usefulness of these models, but right now we will analyze this problem. So, the first few steps are similar to what we have been doing till now. We assume displacement in terms of generalized coordinates and the eigenfunctions, and these eigenfunctions satisfy this pair of orthogonality relations and this eigenvalue problem. This is eigenvalue problem, and this leads to the equation for the generalized coordinates, and the generalized force on the right hand side is now integral 0 to L phi n of x f of x comma t dx, and this n runs from 1 to infinity. A n of t therefore, in terms of the nth the impulse response function for this system is given by this double integral. One of these integral is with respect to space that arises in definition of the load, and the other one is the integral that appears in the Duhamel integral or the convolution integral. This is in time, this is in space. Now, let us look at the moments of a n of t. So, if you look at mean of a n of t, this is expected value of a n of t is expected value of this right hand side, and if you take expectation inside, the expectation now operates on f of x comma tau, and it is specified that the mean of f of x comma tau is 0, therefore, mean of a n of tau is 0. Now, you consider two generalized coordinates a n of t and a k of t, and you consider a n of t1 and a k of t2, and I want now the cross covariance between these two quantities. So, here each one a n of t itself is expressed as a double integral, therefore, when you multiply these two we get 4 integrals here, and the integrand will contain the expectation of f of x1 comma tau 1, f of x2 comma tau 2. For this we have the model, that is, this is given by I naught m of x1 delta of tau 1 minus tau 2 delta of x1 minus x2. So, the integration is on x1, x2, tau 1 and tau 2. Now, two of this integration can easily be done because there are two Dirac delta functions, one in time, one in space. So, if we do that, I get this double integral 0 to t2, 0 to L, this product, and I naught m of x2 phi n of x2 phi k of x2 dx2 and d tau 2. Now, if we now look at the integration in space, what is this? This is actually 0 to L, it can be written as m of x phi n of x phi k of x dx. By virtue of orthogonality property of phi n of x, this is 0 when n is not equal to k. So, what happens is this will contribute only when n is equal to k, otherwise it is 0. That would mean the cross covariance between a n and a k is 0 for n not equal to k, and for n equal to k the auto covariance now of a n of t1, a n of t2 is given by this quantity. And of course, the variance itself is given by you put t1 equal to t2, we get this variance. So, for this excitation, that is this so called rain on the roof excitation, the generalized coordinates become uncorrelated. If excitation is Gaussian, that would mean generalized coordinates are stochastically independent. So, the uncoupling of equations is now total in the sense the equation for a n of t does not contain any terms involving a k of t. In the mechanical sense it is already uncoupled, but in a stochastic sense the generalized coordinate a n of t is independent of generalized coordinate a k of t. So, this type of models affords significant simplification in modeling, and that is sometimes exploited in representing distributed loads like turbulence and things like that. Now, if we return to the moments of displacement y of x comma t, again we have to do the apply the expectation operator on these expressions. So, expected value of y of x comma t is expected value of this right hand side, and that is expected value of a n of t which is 0. You now want covariance between response at x1 and x2, we get this double summation, but we already seen a n of t1 and a k of t2 are uncorrelated. So, this collapses to a single integral, and if you are finding variance of the response, it consists of summation of some kind of weighted sum of variance of individual generalized coordinates. That means, in computing variance of the total the beam displacement y of x comma t, there is no cross terms between contribution from cross terms involving product of a n of t and a k of t. This is only true for the case of this rain on the roof type of excitation. It is not generally true, but many people use that assumption even when the excitation is not of the type that is of the type of rain on the roof type of excitation, but that modeling is inappropriate. So, we will now consider a slightly more general random excitation, where f of x comma t is a random field evolving in x as well as time. It is not a rain on the roof type of excitation, but instead we assume that the mean is 0, but the second order moment f of x comma t into f of x plus I t comma tau is now uncorrelated in space, but in time it is a stationary random process. Okay. Now, the analysis here is reasonably straightforward. We assume y of x comma t again in the terms of generalized coordinates and eigen functions. So, this is given in terms of the double integral h n of t minus tau phi n of s f of s comma tau ds d tau. So, from this I can compute the expected value of the response, and since this is given to be 0, this expected value becomes 0, and I can consider the cross covariance, and if we run through this integration, 2 of the integration we have this expected value of f of s1 comma tau 1 f of s2 comma tau 2, and that appears here as a Dirac delta function in space, but in time it is r of tau 1 minus tau 2. Earlier we had a Dirac delta function here again, but right now it is not so. So, one of the integration can be done easily, and we from 4 integrals we come down to 3 integrals. Again, by using orthogonality relation of this phi n of S2, phi k of S2, we can show that this double summation reduces to a single summation, and this triple integral becomes a double integral. So, some simplification is possible, but here mind you, we are assuming m to be constant and c to be constant. That means, the beam problem that I am considering here, EI, M and C are not functions of x. Earlier I was including that when I consider rain on the roof type of excitation, M was a function of x and EI was function of x and C was function of x. So, with this simplification again we can get this expression with slightly less amount of effort. Now, we already outlined the formulation for response of a beam under time dependent boundary conditions. We will now consider the time dependent boundary condition to be a random process. So, we will consider now a clamped beam with one of the support being subjected to a time function v of t, which is modeled as a stationary random process. So, the governing equation is E I y 4 m y double dot plus C y dot equal to 0. I am assuming E I, M, C etcetera to be independent of x, and these are the boundary conditions. The excitation v of t appears as a boundary condition, and we are assuming the system starts from rest. V of t we take it to be such that its mean is 0 and its autocovariance is a function of time difference, which is r v v of tau, and associated with that there is a power spectral density s v v of omega. Now, given this, the question is what is the statistical properties of beam displacement. what is the mean, what is covariance, what is cross covariance, what is auto power spectral density, what is cross power spectral density, and so on and so forth. So, since the boundary conditions are time dependent, we implement this transformation. This we have discussed just a while before. So, I need not have to go through this, but the logic is displayed here. If we do that, we get an equation for the new dependent variable w, introduce a new dependent variable w and an unknown function of h of x. W is unknown, h is unknown, h is selected in a certain manner such that w becomes, the governing equation for w will have time invariant boundary conditions. So, if we do that, we get the equation for w to be this ei w4 mw dot cw dot equal to a function of x and t, where h of x is this function which we derived just a while before. At this stage, we have now reduced the problem to a form which we have just now seen how to handle. So, this is one approach for handling time varying boundary conditions, and on this we can do now statistics, find out mean and variance, etc. Now, there is yet another approach which is valid when support motions are stationary random processes. Here we do not take the route of using Green's function in terms of system natural frequencies, normal modes and modal damping, but we directly solve the field equation. To illustrate that, we will consider this problem again. To start with, we will assume that the support displacement is a harmonic function. So, the support displacement appears as a boundary condition, and this is a linear partial differential equation, and the excitation source is harmonic. So, as time becomes large, the response of the structure also is harmonic at the driving frequency, but with an unknown amplitude. So, with that logic in mind, I represent y of x comma t as phi of x into e raised to I omega t. Now, phi of x is an unknown function, it is not an eigen function. We substitute this into this equation, we get E I phi 4 minus m omega square phi plus I omega c phi equal to 0, and the prescribed boundary condition on y now translates to boundary conditions on phi, and phi of 0 is 0, phi prime of 0 is 0, phi of L is 1, because y of L comma t is phi of L e raised to I omega t, and this is given to be e raised to I omega t. Therefore, phi of L is 1, phi prime L is 0. Now, I introduce a parameter lambda to the power of 4 as m omega square minus I omega c by E I, and this is now an ordinary differential equation with x as the independent variable. So, it has this simple solution in terms of sine and cosine functions, sine, cosine, sine h and cos h functions. This we have seen when we derived the beam eigenfunctions. The same form of the solution is relevant here, but except that now we have an inhomogeneous boundary condition. This is not an eigenvalue problem. So, A, B, C, D are the arbitrary constants to be determined using these 4 boundary conditions. If we do that, phi of 0 is 0, phi prime of 0 is 0, phi of L is 1, phi prime of L is 0. So, if we put phi of 0 is 0, A becomes 0, phi prime of 0 is 0, C becomes 0. So, A is gone, C is gone, and I am left with B and D, and I have 2 more equations at x equal to L. Phi of L equal to 1 leads to this equation, phi prime of L equal to 0 leads to this equation, and I can solve for B and D from this and get an expression for y of x comma t in this form. So, this quantity which multiplies exp I omega t is nothing but the transfer function, right, and this can directly be used in our random aberration analysis to find out power spectral density of the response and so on and so forth. How we do that? We are interested in the case where V of t is a stationary random process with a power spectral density SVV of omega, and I am interested in power spectral density function say of say y of x comma t. So, SYY of x comma omega is given by, this is the basic definition of power spectral density function, and for YT of x comma omega I use this relation. This phi of x comma omega is nothing but a transfer function which we have derived just now. So, now substituting this into the definition of power spectral density function, I get the response power spectral density function to be given in terms of this transfer function into the power spectral density. So, this solution in fact does not involve any modal expansion. So, more general models for damping can be used. But the penalty that you have to pay is you have to deal with trigonometric and hyperbolic sine, cosine and sin h, cos h functions. So, we can make some concluding remarks on vibration of continuous systems. Why do we study continuous systems? They serve as means of first cut models for a class of structures like tall buildings, soil layers and line like structures such as chimneys and towers. So, in their own standing they have certain worth. For certain problems, continuous models may simplify the problem. For example, continuous models for lattice structures such as towers. Tower is essentially a lattice structure, but we can represent the behavior of a tower by say a Timoshenko beam, and then we can study of a beam like a Timoshenko beam, cantilever Timoshenko beam is a lot easier than studying a huge lattice structure. Another thing is, if loads are rapidly fluctuating or when high frequency vibration is of interest, it may be preferable to use continuous parameter models than discrete models. The most important application of continuous systems is that certain problems can be solved exactly. This is of educational value and also helps in assessing approximate methods of analysis. So, these are some of the reasons why we study continuous systems. In practical applications they are seldom used, but they serve as very useful models for various reasons mentioned here. The limitations of using continuous system models is that for each structural type we have to develop a model. I have been talking about Euler-Bernoulli beam. So, you have to study an axial vibration problem, a beam problem where Euler-Bernoulli beam we discussed, and if you include shear deformation and rotary inertia, you have to develop a theory for Timoshenko beam, and you want to study an arch, you have to combine theory of Euler-Bernoulli beam with axial vibration models, or if you are interested in deep arches, again you have to develop another theory. In 2 dimensions you have to deal with plane stress models, plane strain models, plates, shells and so on and so forth. So, each one you have to develop separately. Even if you achieve all that, built up structures like building structures, a building structure has beams, slabs and maybe trusses as part of the roofs, etc. So, it is hard to imagine how continuous system models can be used in studying such systems. We will end this lecture here. In the next lecture, we will consider problems of reliability analysis of randomly vibrating systems.